Hello, everybody, and welcome to our webinar from HakaGerodur and GHEtool about conical probes and how you can design your borehole field with GHEtool. I hope you can hear me. I hope you can see me. Is everything good? Please let me know if with a thumbs up, with a thumb down, if you can hear us and if you can see us. Yep, good. I see that everything works. So we go direct into the presentation. It's first an introduction about HakaGerodur, who we are, what we do. Then we jump to the next point about the conical probes, what probes we offer, what is the benefit of them probes. Then I hand it over to Wouter, and he will present the GHEtool. The modeling of the conical probes. Then we have two case studies in store where we show you the conical probes and the benefits. And then there are question and answers. But you can always put your questions in the chat. And yeah, we're going to answer that after this webinar. But I completely forget to introduce ourselves. So my name is Sasha. I work for HakaGerodur. I take care of the sales of the Nordic countries. And this is Wouter Pierre. He invented the GHEtool. Yes, good. So the first thing about the company, we have three manufacturing plants. We are an extrusion companies in four different business units. The first one is heating and sanitation. There we manufacture underfloor heating pipes, supply pipes for everything which is leading the water inside the house. You seldom find a HakaGerodur pipe because it's always OEM business. Then we produce pressure pipes for gas, water, drainage, for hydrogen, any media which is needed in the ground. So these pipes are mostly buried in the ground. Then the third division is geothermal. That is what I work for. We mainly manufacture the geothermal probes, manifolds and chambers. And then the fourth division is profiles, plastic profiles for industrial application, for furniture, for windows, and yeah, with different materials. About the story of HakaGerodur, I did it very, very short. So 1932, Hans Kaufmann created Haka AG. 1955, the brother Franz Gebert, the brother of the one which created Geberit, created Gerodur. Then they merged. That's why it's called HakaGerodur. For foreigners, it's very hard to pronunciate. 1991, there was the daughter company of the foundation of the daughter company Neustadt, Germany, Gerodur MPM. And since this year, we implemented the conical probe into GHEtool. So basically, this is what we manufacture in the geothermal division. We manufacture horizontal collectors, manifolds, products for energy piles. Then by far the biggest product is the geothermal probes in different variation. We have conical probes, RT material for rise temperatures. We have 3-layer geothermal probes for contaminated ground if you have gas in the ground. And yeah, for any application we have the right product for the right probe. But here we focus on the conical probes. Then we also do manifold chambers, which are buried in the ground, and all the connection pipes and parts needed to hook up the borehole field to the heat pump. So the conical probe Vario Flux, what is special about it? For a cylindrical probe, you have the inner diameter all the way through. So the inner diameter at the top of the probe is the same as on the bottom of the probe. With the conical probe, the upper diameter is bigger and the lower diameter at the U bend is smaller. So there you have a bigger wall thickness where you need the pressure resistance. Let's say if you're 300 meters in the ground, the ambient pressure is 30 bar, and there you cannot have a small wall thickness because otherwise if you grout it, then you squeeze the probe. So what does that bring? The media, the brine or the water has less restriction in the upper part of the probe, so you have reduced pressure drop. So the brine is less restriction and your circulation pump doesn't need as much power to push the fluid through. So that's the whole magic. And for bigger projects, you can also size the circulation pump smaller. But anyway, if you have this product, the circulation pump doesn't need as much power to push the fluid through. So you have energy savings of, depending on the project, up to 65%. And for a bigger project, you save thousands of euros every year. For the drillers, that might be not that interesting because they just like to drill a borehole, put the probe in and grout and leave. But for the operator or for the designer, this is a very interesting product. So here we come to the standard duplex probe. The material is P100RC. We manufacture them in PN16 and also PN20. The U-bend is always PN25. Doesn't matter if it's PN16 or PN20. We have different diameters. What we produce this, where we produce this probe, it's 32, 40, and 50. Length up to 500 meter. We also do customized products, but yeah, it doesn't make sense with to go deeper with a cylindrical probe because we have the conical probe which have much more better efficiency because of the conical style. On every probe there is the double metering where you see how deep you are and also the direction indication. So every meter we assign our pipes. Then we come to the conical probe. This is the Vario. It's available up to 250 meter. For customized products, we can also make it longer. On the right side, you see how it looks like. So the top is with a smaller wall thickness, so you have more room in the inner diameter, and on the bottom it's a thicker wall thickness, so less room in the pipe. The material is also P100RC, pressure rating PN16 or PN20. The probe foot is also PN25. And this year we also created a Vario probe which is rated up to PN25. So we started PN16 going down to PN25. It's also available in 32, 40, and 50 millimeter. And there is also a patent for this product. We're gonna see later in this webinar a project, how we designed it and what is the savings. So we come to the next probe. This is the flux probe. It's we say it's from 240 meter till 600 meter. The standard one is till 500 meter. We have it available. Two different pipe diameters. We have one with 43 millimeter and 53 millimeter. The 53 millimeter is for deeper boreholes. and the pressure rating is 32 or 38 bar, depending on which product you choose. There is also a patented product, and as you know from HakaGerodur, it's every meter is there is a signature with the double metering, the production date, flow direction that you hook it up right. And it's a SKZ certified product. So as all our products are certified, the whole system. So now I hand over to Walter, and he explains the situation, the history of GHEtool and what it can do.
Okay, thank you, Sasha. So for some of you who might not yet know GHEtool, a couple of words about it. Now, a very brief history. We're also not that old as HakaGerodur. We are founded in 2019 during my master thesis at the KU Leuven in collaboration with Boyden's Engineering, which is now part of the Swico family. In 2023, we released GEtool Pro to see if there was a demand for another design software in Belgium. And there was quite a lot of positive feedback. So in November last year, it's almost a year now, we released GHEtool Cloud, which is the software we will be using today for the case studies. And just to give you some numbers, in less than a year, we went up to 64 licensed users. Yesterday, we have more than 400 companies trialing the software. At this moment, we are currently market leader in Belgium since the summer of this year, and the goal for next year is really to go for internationalization. We already have licensed users in more than 6 European countries, and we like to spread our message even further. Now, why do people change to GHEtool? Because there are other alternatives available on the market already for quite some years. And there are basically 3 reasons we asked our customers, and they gave us 3 reasons. And that's because it's a tool for 2025. It's a catalyst for innovation, and we help you design with confidence. Now, why are we a tool for 2025 and next year for 2026? It's because we have a lot of updates. We update around once every week. The last update was from last week. So we guarantee you work with the latest and most accurate scientific models to get the best results as possible. But then next to that, we also focus on giving you a powerful tool, but easy to use, because geothermal design is complex enough on its own that you don't need a complex software to handle this complexity. So we have scenario analysis, automated reporting, everything to make your life easy. And we have also methods to help you design projects until 2025, because the geothermal designs are not the same as 20 years ago, and some software are. So we have added methods for pressure drop calculation, which we'll be using later this webinar. We have hybrid system designs, air and water source heat pumps. We can work with the most complicated designs, tilted boreholes, whatever. It's a really flexible software. And the second reason is we believe in innovation, but we also believe we can't do it alone. And we are just a software in that sense. And we try to work a lot with industry partners. So we have a couple of companies that already partnered with us. 2 companies that produce alternatives to glycol and to antifreezes. We have 2 heat pump manufacturers who will be publishing their data into GHEtool next year. The date is not yet decided, but it will be. We have 3 probe manufacturers who have developed innovative heat exchangers. We have also worked together with them to develop methods and to make them available in our software. Of course, we work together with universities all over the world, quite a lot for teaching, but also for research, developing new methods, new models, and really drive this innovation forwards. And the third thing is that having a great software is one thing, but we also want to educate our designers, our drillers, how to use it, but also how borefield physics work. So we have a whole YouTube channel with more than 10 hours of me talking. If you're interested or you want to have a good night's sleep, you can always go to our YouTube channel listen to some geothermal information, some case studies, some physics. We have articles on everything, more than 300 pages already, with also an article at the beginning of last month about what we're talking about today, the modeling of the flux and the vario probe. So quite a lot of information there. And if you want to talk with us and about models or future updates, we also try to be on as many expos and symposia as possible. So next week we will be in Salzburg. 2 weeks later we will be in Frankfurt, and then in February we'll also be at the GEROtherm Expo in Offenburg. So please come and see us. So basically, to summarize, these are some words of our users. We don't see ourselves as a software, but we see ourselves as a community where users, companies, industry, and universities work together to bring the best geothermal design software to the market. So if you're ready for it, if you want to level up your design game, please get in touch and be part of this fast-growing community around GHEtool. So that were a couple of words about the software. But now let us jump into how we modeled the vario and the flux probe, which Sasha introduced. And then we can go to some examples and see how you can design real-life projects with it. So basically, if we look at this pipe, it's basically 3 regions. And we have a first region where the wall thickness is constant, and for that we know the solution. And the last part is also has a constant wall thickness, and for that we also know the solution. But it is conical part that's really the innovation for which we had to develop a new scientific model. Now we can say, well, of course it's going linearly, the wall thickness. Why don't we just take an average value? And the problem with that is that everything related to borefield design and hydraulic design, the Reynolds number, the friction factor, the pressure drop, the borehole resistance, it's not linear. And for example, if we say the Reynolds number, it depends on the pipe diameter, the inner pipe diameter, but also on the flow velocity. And this flow velocity also depends on the inner pipe diameter. So for all these important parameters, the equations are not linear. So it's not as easy as just taking the average value. And that's why we went for something which looks a little bit more complicated, which is called the mean value theorem. And without going too much into the mathematics, basically what this function does, this method does, is we take the integral under the curve, under what we're actually calculating, and we're trying to find a rectangle with the same area. So in that way, we can take the non-linearities into account and make a way more accurate average or a mean value. And the difference can be seen on this slide. So just taking the standard average value gives you the blue line, and the orange line is with the more accurate methodology. And now you might say, okay, the difference is not that big, but all these factors, the Reynolds number, the borehole resistance, they all interact with each other. And when you take into account that the flux probe can up to 600 meters deep, this variation can become quite significant. So that's why we chose to work with the more accurate mean value theorem. Now, more interesting is actually how it behaves thermally and hydraulically. So this is the pressure drop curve for flux DN53, ranging from 0 to 500 meters. And we see 3 lines here. We see the green line, which is basically the pressure drop in when we have the first section, the first wall thickness, all the way down to 500 meters. It's a theoretical exercise, of course, because, yeah, 500 meters with the PN14 wouldn't be a good idea, but imagine it would go down to 500 meters, you have the green line. Then you have the orange line, it's the bottom section, where we have a thicker wall thickness, so of course the pressure drop is higher there. And also if we would extend this over the whole pipe length, we get this orange line on top. And then we have our flux probe, which is the blue line. And we see that for the first 180 meters, I believe, from the top of my head, it's exactly the same as the regular probe, because, yeah, this first section is exactly the PN14. And then it starts to diverge because we're getting conical. The average inner diameter decreases, the pressure drop increases, and so we're going more parallel with our regular PN38, but there is still a significant difference in pressure drop. Now this is for a constant flow rate. If we say, okay, let's take a pipe of 500 meter and let's vary the flow rates. And here you can see clearly that our flux probe is in the middle of both our two edge cases, let's say, where we see that our regular PN38 would transition to turbulence sooner. That's this sudden jump. And that's, of course, because the wall thickness is thicker, the inner diameter is a little bit smaller, the flow velocity is a little bit higher, so it gets to turbulence sooner. The flux probe, it starts at the same point getting turbulence, and of course, because it's conical, it takes a while before the larger inner diameter gets turbulence. So that coincides with the PN14, and then it follows the same quadratic curve for turbulence pressure drop. But the most important thing for you is that you see that due to this conical design, our pressure drop is always in between the two extremes. And that's an interesting thing to notice. And then we lastly have the borehole resistance. So a measurement for how good the borehole or the pipe can exchange energy with the ground. We have again the three cases, and we see here in the beginning everything is laminar, so everything is really close together. We see here a certain bend in the curve. That's where our regular probe gets regular PN38 probe gets turbulence, so it goes down a little bit. So it's the best here, but it's negligible, let's say. Somewhere in between, our flux probe also gets turbulence, and then our theoretical PN14 also becomes turbulent. And what you can see that in this turbulent regime, which you typically have if you're drilling 500 meters deep, our flux probe is also outperforming the regular PN38, which might seem strange because we just said, well, the regular PN38, it has on average a smaller inner diameter. So on average, the flow rate is higher. So the turbulence is higher. But the thing is that once you are turbulent, it does not really matter that much whether you're a little bit turbulent or very, very turbulent. So once we are in this range, it's actually the average wall thickness that plays an important role. And since the flux has a conical design and hence on average a smaller wall thickness, the heat transfer in this turbulent regime is actually better than the regular probe. So also from a thermal point of view, for higher flow rates, for higher Reynolds numbers, the thermal performance is better than with the traditional regular smooth pipe with the same pressure resistance. So now I hand it back to Sasha to introduce two cases, and then we will take a look at how this theoretical graphs now relate to real-life projects.
Yeah, thank you very much, Wouter, for your explanation. We come now to two projects, what we did, what we made in the past. The first one is a project with the Vario probe PN20. It's made apartment building made in Rapperswil, Switzerland. So on this page we see we had 4 probes, 225 meters. PN20. In total, it's 900 drilling meters. The demand for heating is 44 kilowatts, so it's 85 megawatts per year. And the domestic hot water is 20 megawatts per year, so there is no cooling. And here we see on the upper part for the simulation parameters, we use a brine. So now we go to the GHEtool, and Wouter show you how to use the GHEtool.
Perfect. So let us go ahead how we can translate these parameters into our software. So without going too much in detail, we created a couple of scenarios. So the first case is in Rapperswil. And we will first take a look at the traditional DN40 probe and then compare it to a VARIO. So what we did is we calculated the temperature profile with a minimum and a maximum average fluid temperature. And we also calculated the pressure drop. All the pipes were collected in parallel with certain distances from the borehole to the manifold and to the plant room. The ground properties, it was close to Zurich, so we used these values. For the borefield, it was just everything in one line with 225 meters, as Sasha told you. For the borehole resistance, our first case is our traditional DN40 PM20 probe, an SDR of 9 with monoethylene glycol and a certain flow rate. For thermal demand, just to show that everything was right, a certain power. Someone is at the house, but it's not important. A certain power and then a certain energy demand as well. So if we then go to the results, we have a couple of numerical results here. We see that we go towards minus 1.16 degrees after 50 years, which is above our design limit, so it's good designed. We are both in a turbulent regime, and the pressure drop across our single borehole is 107 kPa. Or if we scroll down, we see the hydraulic design, and we see that we have here an estimated pump energy of around 970 kilowatt hours per year of electricity consumption for the pump. So this is the situation for our traditional probe. Now, if we go to our resistance step, and we would say, well, use the GEROtherm VARIO instead. Everything else stays the same. If we now go to the results, we see that we now go to -1. So it's a little bit higher in temperature than we had before. And that's because our borehole resistance, as you can see here, it's 0.0832. It's here a little bit higher. So our thermal performance from the VARIO is a little bit better. But what's more significant is that here we have only a pressure drop of 90 kPa instead of the 100 N. And this relates to only having a pump energy consumption of 830 kilowatt hours per year instead of 960. So you can see that this conical design for this project actually improved our design by 15% plus or minus in pump energy consumption, and it saved even a little bit, or it gave us a little bit a higher average fluid temperature as well. So let me go ahead, jump back to the slides.
So thank you very much, Wouter. So then we come to the next project. It's made with the flux probe. We have 12 flux probe PN32. It's a project in Germany, in Sachsen. It's a new school and a sport facility. Here are the details. We use a brine water. The heat demand was 200 kilowatts, 483 megawatts per year. A domestic hot water 34.2 megawatts per year, and the cooling was 35.3 megawatts per year. So here we have, as mentioned before, 12 probes at 350 meters, so total of 4,200 meter W probes, 43 PN32. Fluid is also a brine, and the ground thermal conductivity is 3 watts. So the average temperature in the ground is 15.8 degrees Celsius. So now we put all these figures into GHEtool.
And let's see what comes out of it. So same thing here. It was a different region, different design parameters. So here was it -3. On ground, it was measured at, it was a TRT test done, so we just entered the undisturbed ground temperature directly, our conductivity. We now have 2x6 boreholes, so 12 of 350 meters borehole length. And for our borehole resistance, our comparison to this case, of course, there is no 32 PN32 regular probe. So we created a theoretical one, so with a DN40. If we would have had PN32 DN40 probe, it would have had this parameters. So it just has a theoretical comparison. We have a 30% of monopropylene glycol and a flow rate. Our thermal demand here we have some yearly cooling for the regeneration. And if we now go to our results, we see the following graph. Here we end up with a system that goes to minus 0.61 degrees Celsius, a borehole resistance just more than 0.1, and a pressure drop of 542 kPa, which is rather high. If we then go towards the hydraulic design on the bottom, you see here that for design flow rate, we have an estimated pump energy consumption of 37 megawatt hours per year of electricity usage. It's a deep borehole, it's quite a lot of flow, quite a high pressure drop and pump energy as well. Now, if we go to our borehole resistance step, and if we would change it to the GEROtherm FLUX probe, the DN43 PM32, all the parameters stay the same. We see here again that our average temperature is a little bit higher. Our borehole resistance is a little bit better, which I explained because the wall thickness is on average a little bit smaller. But what is important is that our pressure drop is now significantly lower. So we came from 540, we are now at 190 kPa. So our electricity consumption is now only 13,000 kilowatt hours per year, instead of the 37,000 kilowatt hours per year. So that's, for these deep boreholes, quite a significant difference, having this average smaller wall thickness in this case. So if you have questions afterwards, feel free to ask them, but I will give the word back to Sasha to wrap this webinar up, or the official part, and then we can continue with the discussion.
Okay, thank you very much, Walter. So yeah, this is more or less what we planned for this webinar. If you have a further question, or if you want to help with your own design, if you want to see what the conical probe does for your project, you can schedule a free demo for GHEtool. You have 1 month free usage of GHEtool. And for all the questions, Walter would help you and assist you with any questions. So then I say thank you very much for your attention. Great to have you here. And now we are open for the questions, if there are any. Thank you very much.
Let's close this and see if people have any questions. Are there any questions? You can pop them in the chat. I don't see any questions yet.
So if there are no questions, then we presented it very clear. Thank you very much. And I hope to talk to you soon.
Yeah.
Thank you very much.
Take care.
Bye-bye.